Good morning, good afternoon, and welcome everyone to the third Consciousness and Reality Colloquium for this academic year. I'm Kunal Mule, an astrophysicist and the co-founder of IMIX, which is the Institute of Mind, Intelligence, and Consciousness Studies. Christoph Koch from the Allen Institute is our co-host, and we have participants today from across Caltech, MIT, Stanford, Berkeley, University of Arizona, and IMIX. The CNR Colloquium series seeks to inspire interdisciplinary investigations on mind, cognition, consciousness, and the nature of reality. Before we introduce our colloquium speaker today, I request all of you to please note that Q&A button at the bottom of your Zoom window. You can post your questions by clicking on that button, and selected questions from the Q&A box will be taken after the talk. And we're going to make this, like previous colloquia, make this more interactive and fun. You will see the poll button at the bottom of your Zoom window, and click that button to answer two simple yes/no questions. I'm going to launch the poll right away. And yeah, here it goes. So as you can see, two binary choice questions. Question one is, despite being warm, wet, and noisy, the brain could harbor quantum information. And question two is, mental processes may be associated with quantum phenomena. So looking forward to this talk. I will announce the results of the poll at the end of the talk. And I now request Christoph to please introduce our esteemed speaker, Matthew Fisher.
Good morning or good afternoon, everyone. Thank you, Kunal. I'm Christoph Koch. I'd like to introduce our today's speaker, Professor Matthew Fisher. He's a theoretical physicist, obtained his PhD in Urbana-Champaign, and then is a faculty member at UCSB for for almost a third of a century now. I think he joined in
1993.
93, yeah, so that'll make it 32 years. He's a well-known member of Academy of Sciences. He's well known for his work on many-body quantum information theory, non-equilibrium quantum dynamics of open system and other and monitored quantum systems. But in today's context, he is best known for a paper he published, I think exactly 10 years ago in 2015 in the Annals of Physics, where he proposed something at the time that was and still is considered, certainly by my colleagues, I'm a neuroscientist now, quite radical, which is the title of the paper was Quantum Cognition, the possibility of processing with nuclear spins in the brain, as the vast majority of biologists assume the brain is, as expressed by the poll that Kunal asked us all to answer, is warm and wet, and any quantum effects will wash out. But Matthew differs, or at least has a very interesting testable hypothesis on how this could be wrong, and how nuclear spin could be a critical quantity in biology in general, and maybe in cognition and consciousness in particular. Matthew, take it away.
Okay, thank you so much, Kunal and Christoph. Let me share my screen. Can you see see the screen here? Let me
Yes, we can.
Get a spotlight. And let me make sure I can change the slides. Okay, well, thank you so much. Yeah, so I'd like to describe an ongoing story which started over 10 years ago. And the question, has been, could there conceivably be quantum processing in the brain? A subtitle might be, are we quantum computers or merely clever robots? Now, I'm going to take you through the way I ended up getting interested in this question, and then describe the sort of scenario behind our thoughts on this, and then tell you a bit about some of the experiments, and then finish with some, very loose speculations about relevance to consciousness and, well, reality. I think it's relevant too. Okay, So the story begins not with quantum mechanics or quantum mechanics in the brain. It begins with lithium. Now, lithium is an atom. It has two stable isotopes. Let me remind you, lithium-7 has 3 protons and 4 neutrons in the nucleus. It's 92% natural abundance. So most lithium that's in your lithium-ion batteries is lithium-7. Lithium-6 is the rarer isotope of lithium with 8% natural abundance, and it has 3 protons and 3 neutrons. So they differ just by 1 neutron in the nucleus. The lithium-ion, lithium plus, has just 2 electrons in the 1s shell, and so they electrically are identical. But besides being an atom, lithium is a remarkable drug, and I've had personal experience with this, as have many people throughout the world, as a treatment for psychiatric disorders. It's most effective for bipolar disorder, and it's been used extensively for that purpose since 1970. So I've always been interested in the psychiatric pharmaceuticals, which, modulate the tenor of one's conscious state. That's what they do. And so being influenced by these drugs in a very positive way, one can't help but think about, implications possibly for one's conscious state. So one can ask, how does lithium work? It's just a single atom, you ingest it. But in fact, how do any psychiatric medications work? And I'm not sure we really understand any of them. And in order to really understand them, I think we have to understand ultimately the biochemical underpinnings of consciousness or sentience. If we want to treat that, you really need to understand it. So about 12 years ago, I had what I thought was an interesting question or suggestion, which is to take the 2 lithium isotopes, isotope purify. You can buy 95% lithium-6, or you can buy 99% lithium-7, and to feed the lithium isotopes to rats and ask whether there are any behavioral manifestation on the rats, any behavioral differences. And in the most remarkable day in my scientific career, I discovered this experiment was actually tried in 1986, and the results were so surprising as to be, very suspect, but they were in some sense kind of amusing. So I'll show you very briefly, a summary of what they found. They were basically looking at, among other things, the mothering behavior of rats, and they took a number of rats, I think it was 24, divided them into 4 groups. One group they gave naturally occurring lithium, that's lithium N. Another group they gave isotope purified lithium-7. A third group they gave lithium-6. And then a control group they didn't give any lithium to. And lithium takes a number of weeks to start being effective, at least in people. And so these rats were doped up on lithium, I think, for certainly a number of weeks. And then they impregnated these rats and looked at their mothering behavior. And this was very non-quantitative. As you can see under the column behavior, they looked at nest building, nursing, grooming of pups, retrieval of pups, grooming of self, and so forth. And the control pups were all average. Now, I have no idea what average means, but it's some subjective notion that they must have observed. Now, naturally occurring lithium rats or lithium-7 rats, and remember, lithium-7 is the most abundant isotope, so one would expect them to be roughly the same. And these rats, these mother rats, were sort of dumbed down. The nest building apparently was completely absent. Nursing was infrequent. Grooming of pups was infrequent. Reaching for food infrequent, and so forth. The remarkable column, which I now displayed on the right, was the rats who were doped up with lithium-6. And as reported, the nest building was excessive. Nursing was very frequent. Grooming of pups excessive. Basically, the mothers that were doped up on lithium-6 were super moms. Maybe they were even helicopter parents. And it's quite remarkable, this experiment, because the difference between lithium-6 and lithium-7 is one less neutron in the nucleus. Now, I've been very suspicious of the results of this experiment. It's not quantitative at all. And so I've been trying to encourage this experiments along these lines to be repeated. And I convinced Aaron Ettenberg, who's actually recently retired at UCSB, to try the following experiment. So he was looking again for differential lithium isotope effects on rat behavior, and using a ketamine rat model of mania. So it turns out that if you inject a rat with ketamine, it makes them, quote, manic. They run around a lot. And in this plot, you can see the distance that they ran around, distance traveled as a function of time. And then they took 5 different groups, a group in which they just gave sodium chloride, a group with the rats where they gave lithium-7, a group lithium-6, and a group of naturally occurring lithium. And then here's a non-ketamine control. They injected these rats with ketamine, and they looked at how much they traveled around. And you can see that the non-ketamine controls didn't run around that much, and all of the rats that had ketamine, ran around significantly more, particularly in this intervening time between about 20 and 35 minutes. But remarkably, we found, or Aaron Ettenberg found, that lithium-6, the ketamine-induced mania was suppressed, significantly more than in than lithium-7 or naturally occurring lithium, and certainly compared to the sodium chloride with no lithium. So one might want to conclude that lithium-6 could be more effective at treating mania than lithium-7 or its parent compound. I think, ultimately one would like this to be tried in human subjects, but that's another story. So there seems to be this.
Were these people blinded to which, were the experimentalists blinded to which lithium the rats were on?
Yeah, they certainly were.
Okay,
yes.
good.
Yeah. I mean, this was done with some care, I think. I was sort of following along on the sidelines at the time. Thanks. So how could one have a lithium isotope effect? Now, I write classical or quantum question mark. The knee-jerk reaction to why lithium isotopes would have a differential effect would be, well, wait a second, they have a different mass. Lithium-7 weighs a little bit more than lithium-6. Lithium-6 is lighter, and it might diffuse around a little more quickly when it's solvated in water. But these diffusion constants have been measured, and they only differ by about 6 parts in 1,000. So there's very small differences in the diffusion. So, that would be a classical effect, and it seems, rather unlikely. Now, lithium presumably gets taken up into cells, into neurons, and it must pass through sodium or potassium channels. And you could imagine that in the tightest place as it passes through the channel, there's a little bit of quantum tunneling that's going on. And quantum tunneling rate, gamma here, depends on the mass. And so one might expect then lithium-6 to tunnel a little more frequently and get into the tissue at a higher concentration. But experiments have been done looking at whether there is any differential tissue uptake of lithium, the 2 isotopes, and none has been reported. So that doesn't seem to be what is going on. And the third difference between nuclear lithium-6 and lithium-7 are the nuclear spins. And I'll come back to this in a moment, this time T lithium-7 and T lithium-6 in a second. But this experiment, really got me thinking, could there conceivably be some quantum processing going on in the brain? Now, the reaction of, I think almost all scientists, certainly physicists, would be, there's no way this could happen because the body is simply too hot for quantum mechanical effects. The atoms, the molecules are sloshed around in this wet environment in biology. So how could quantum processing be taking place? It would be decohered immediately. But this assumes that the quantum degrees of freedom, the putative quantum degrees of freedom that might be working being used for quantum processing in the brain are in thermal equilibrium. And in the worldwide efforts to build quantum computers, one thing we know is that you need to isolate the qubits, the quantum mechanical bits that carry the information. They have to be isolated from the environment. And so if one's going to have any quantum processing in the brain, I think one needs to find some degree of freedom in the wet environment of biology, which is isolated. So the quantum processing requires isolated qubits. And what is most isolated from the wet environment in biology by orders of magnitude and in timescales are nuclear spins. So protons and neutrons inside the nucleus have spin 1/2. Some atomic nuclei have spin coming from the protons and neutrons. And if you take a salt like sodium chloride and dissolve it in water, the sodium ions come off the chloride ions, and you can use nuclear magnetic resonance to measure the nuclear spin of the sodium ion and measure the relaxation time or the decoherence time of the nuclear spin. And that's around 1/10 of a second, which is short on human time scales, but is long on microscopic time scales. Lithium-7, on the other hand, has a decoherence time of 10 seconds, and lithium-6 has this whopping decoherence time of about 5 minutes, which we understand why this is. It's because its nuclear spin behaves as if it's a nuclear spin 1/2. But once I saw this, I thought, that's remarkable. This is on human time scales. So could there conceivably be quantum processing with nuclear spins operative in the brain? Okay, so let me turn to that. Nuclear spin quantum processing in the brain, question mark. Well, the approach I've been taking is listing a set of conditions that must be satisfied, at the very least, in order for this to have evolved. We certainly need a neural qubit. We need a common biological atom with nuclear spin 1/2, because they have longer decoherence times. We need an atom in a small molecule that can tumble in water. That's important also for giving long decoherence times. And ideally, the other atoms in the molecule should have a 0 nuclear spin. So the approach I'm taking is one of reverse engineering. And let me just go through some of these questions. So the first one is a common biological atom with nuclear spin 1/2. So I've listed the common biochemical elements, CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and the common bioelectrical ions, sodium, potassium, calcium, chloride, and magnesium. Which of these have nuclear spin 1/2? Well, it turns out besides the proton, which I'm not going to be thinking about because it's, occurs in water and it's everywhere, is phosphorus. So phosphorus is the only common biological element with a nuclear spin 1/2. And phosphorus comes in one isotope, phosphorus 31. And so in some sense, at least in my reverse engineering approach, it's the only possible neural qubit. And if phosphorus 31 is not taking part in any sort of quantum processing, I'd be very skeptical that there is quantum processing that would be present. Now we need the nuclear spin, the common biological element with the nuclear spin, namely phosphorus, in a small molecule that can tumble. And of course, phosphorus occurs in the phosphate ion, surrounded by a tetrahedral shell of oxygens. And now one can put sodium phosphate in water and measure the nuclear spin relaxation of the phosphorus nuclear spin, and it's a modest time of 1 second. I had thought this was going to be longer because of the protective shell of the oxygens, but the reason it's only 1 second is because protons from the water bind and then unbind repeatedly from the negatively charged oxygens in the phosphate ion. And the proton nuclear spin couples to the the phosphorus nuclear spin and leads to a relaxation process and a decoherence process of the phosphorus nuclear spin. So I could have given up at this stage, and I thought about it, but then I said, wait a minute, maybe there's another positively charged ion in biology which could outcompete the proton in binding to the phosphate. So you can look at the other positively charged ions, the sodium and potassium, which don't take part, as far as I can tell, in any biochemistry whatsoever. They don't form chemical bonds. There's magnesium 2+, which does take some role in ATP phosphorylation, but it doesn't bind that strongly to the oxygens of the phosphate. And that left one positively charged cation, calcium. And calcium is an important, of course, element in biology, and particularly in neurological setting. And it had been known for some 30 or 40 years, at least there was some evidence for a calcium phosphate cluster. Well, I should say calcium phosphate is in a crystal form is what teeth is made of and what bones are made of. So there's a lot of calcium phosphate in the body, but there seems to be in solution, if you just put calcium and phosphate in solution, formation of a small cluster, the Posner cluster or the Posner molecule, which consists of 9 calcium ions and 6 phosphate ions, and this is about 1 nanometer diameter. And so experiment we set out to do was to do dynamic light scattering, this is at UCSB, to try to see whether we could find in vitro evidence for a 1 nanometer cluster of calcium phosphate. And we see a big peak there under conditions appropriate for the intracellular fluid. So this Posner cluster would be very suitable for long 31 nucleus spin 31 coherence times, and even rather conservative estimates give minutes, and more, I think, realistic estimates gives decoherence times of hours. So the phosphorus nucleus spins are extremely well protected. They would be extremely well protected in these Posner molecules. So the Posner molecules would be almost ideal for quantum storage of information. Where do Posner molecules occur? In vivo, and the place they believe to occur is in mitochondria. Now, mitochondria, of course, are in all cells. They're a very common organelle, known as, as I learned in high school biology, as the powerhouse of the cell where ATP is synthesized. But mitochondria have another role, it turns out, perhaps less well known, as a buffer and of calcium in the intracellular fluid. When an action potential comes down an axon and reaches the synapse, calcium channels open, and the concentration of calcium, which is in the extracellular fluid, is high, comes rushing in, triggers neurotransmitter release. But after that has happened, there has to be a way to lower the concentration of the intracellular fluid of calcium. And one way that occurs is through calcium pumps, which pump calcium out of the cells. But also calcium is buffered in and taken into mitochondria. And so there's quite a high concentration of calcium in mitochondria. And by drying out mitochondria and looking, one can see that it's actually, the calcium is stored in calcium phosphate, which, remember, was the ingredients of the Posner molecule. So we think that inside a mitochondria might well have a sort of a sludge of many Posner molecules. And the other thing about mitochondria is they're very dynamic organelles. They fission and fuse, they move up and down microtubules. There's some dance that they undergo being distributed around the cell, which is, rather elaborate. It certainly has some function. But we then conjecture that perhaps Posner molecules forming and melting inside mitochondria could entangle non-locally in mitochondrial networks via fusion and fission. Now, even if there were nucleus spins inside phosphorus nuclei in these calcium phosphate Posner molecules inside mitochondria, so what? One would have to have some way for the nucleus spin states to modulate chemical reaction rates. And this would be required for a quantum to biochemical transduction. Ultimately, all of neuroscience is, driven by biochemistry, and unless the biochemical setting the biological setting can be used to read out the nucleus spin states, what's happening in the nucleus spin states doesn't matter. So we need nucleus spin states to modulate chemical reaction rates. And there's a theoretical work that I developed with Leo Radzahovsky, which is based on symmetry and Fermi statistics, If the Posner molecule has threefold symmetry axis, which density functional theory calculations suggest that it does, then one can characterize the nucleus spin states by a pseudospin, which can take on three values, which dictates the rotational angular momentum. And the quantum dynamical selection conjecture conjectures that small symmetric molecules, like the Posner molecule, they're tumbling around, but they cannot stop rotating and chemically react unless this pseudospin is zero, essentially unless the angular momentum is zero. And so where the nucleus spin states could modulate the chemical reaction rate is in the binding of two Posner molecules together. Density functional theory calculations reveal that if you bring two Posner molecules together, they will form a weak chemical bond, lowering the energy by half to an electron volt. So if these Posner molecules are tumbling around and they chemically bond together, under the quantum dynamical selection conjecture, that's only possible if they form what I'm calling a pseudospin singlet. So the nucleus spin states in the two Posner molecules become coupled to one another. So this, if it's going on, would lead to another feature of quantum mechanics, which would be necessary besides storage of quantum information, which is quantum entanglement and non-local quantum entanglement. So the idea is that two Posner molecules come together, they approach and collide. Two things can happen. They could bind together, which makes a projection onto the pseudospin singlet, and then come apart. And when that happens, their pseudospins sum to zero. They become entangled. Or they could try to bind together and fail to bind, and then the pseudospins would not sum to zero. So in this way, two Posner molecules might become pseudospin entangled, which I'm depicting schematically here. And so inside the mitochondria, one imagines this sludge of Posner molecules forming the calcium phosphate inside the mitochondria. And one would have then conceivably networks of pseudospin entangled Posner molecules, depicted sort of schematically here. And the beautiful thing about quantum entanglement is that it correlates and influences non-local processes. So if A and A prime Posner molecules are entangled because they've become chemically bonded, let's say in the past, and B prime are entangled, then if A binds with B, it's more likely that A prime will bind with B prime. There's correlations between the subsequent pair binding of A and B and A prime and B prime. Well, why should this pair binding matter? Well, once the Posner molecules are bound into a pair, as shown schematically here, the pair will dissolve more easily when the pH is lowered. Now, in the mitochondria, the pH is going up and down, as the proton pumps into the mitochondria and to power the ATP machinery. So when in the down cycle, when the pH is low, these calcium phosphate clusters can dissociate, and if they're bound together, they would conceivably dissociate more readily. And if they dissociate, they can release free calcium ions from the mitochondria into the intracellular fluid, which can modulate conceivably neural activity for these mitochondria near synapses, and creating a quantum network that coexists with the neural network. So this is a story, and any story like this needs to at least be addressed by experiments to see whether the different pieces of the story hold together in any way.
Matthew, before you come to that, so the entanglement would only occur within a single among the Posner molecules would only occur within a single mitochondria, right?
When it would occur in a mitochondria, but the mitochondria are fissioning and fusing, all the time. And so if you've got entanglement within a mitochondria and it fissions, you would have entanglement between two fragments of the mitochondria. And then when the mitochondria come back together, then...
But that would be at a subcognitive time scale, right? That presumably takes tens of seconds for the fission and the fusion, right?
Well,
mitochondria.
maybe seconds, maybe less than tens of seconds. You know, it is fairly slow, but you know, distributing the entanglement can take a long time, and using the entanglement can happen more rapidly, right? And so the idea would be that, you know, fragments of mitochondria which are entangled would be, you know, moved around to different places in the neuron, maybe different synapses, and then you could get possibly correlated neurotransmitter release at different synapses.
And so this would still ultimately be an intraneuronal mechanism, right? You would not entangle across neurons.
I don't see that this would lead to an entanglement across neurons. I mean, there are nanotubes connecting different neurons, which do allow small molecules to pass, and they actually allow even fragments of mitochondria to pass through. But I think that's, you know, we think that's probably fairly infrequent. But were that used, one could conceivably get interneuronal entanglement. But I think that's, you know, that seems unlikely.
Okay, thank you.
Okay, so yeah, thanks for the question. So let me come back to experiments. Well, the first experiment, and I've already mentioned this, was an attempt to image the Posner molecule using dynamic light scattering, and we observed evidence for a nanometer scale calcium phosphate cluster, and it occurs in the pH and ion concentrations which are appropriate for the intracellular fluid. You know, pH, there's a window of pH where you see this, which is between 7 and 8 or so. The other experiment, which I'll mention, is trying to test this quantum dynamical selection. That was the conjecture that nuclear spin states could modulate chemical reaction rates. And the other set of experiments we've been focusing on is probing lithium isotope effects in vivo and in vitro. You know, I've already described how in vivo, in rats, there's some behavioral differences. So we want to look at whether there are lithium isotope effects inside mitochondria, whether there are lithium isotope effects in calcium phosphate formation, to try to bridge across, you know, different length and time scales. So as far as the quantum dynamical selection, the nuclear spin states modulating chemical reaction rates, we've been starting experiments looking at a stand-in molecule for the Posner molecule, a biochemical molecule called trimethylamine. It consists of a nitrogen atom with 3 methyl groups, and there's a enzyme which catalyzes an oxidation reaction where trimethylamine becomes a trimethylamine oxide. The oxide bonds onto the nitrogen atom. But this chemical reaction, if, you know, as it comes into the pocket, it has to bind to the enzyme. It has to stop rotating. It binds into the enzyme. And this would be blocked unless the pseudospin is 0. So it'd be actually hard to react. So what is how could we see the possible nuclear spin effects on this? Well, what we can do is we can isotopically label one of the 3 carbon atoms with a isotope carbon-13. So here's a trimethylamine with 2 carbon-12s and 1 carbon-13. That no longer has 3-fold rotational symmetry, and so it would not be blocked anymore and would, if this is correct, react more rapidly, and the products of the reaction would then be enhanced in the concentration of carbon-13. So this is an experiment which we've been, you know, ongoing, and we should have results of this hopefully within 6 months, and you know, teaming up with an enzymologist on this. Okay, let me come back to to lithium, I've already seen, showed you this lithium isotope dependence on ketamine. But how do lithium isotopes fit into the whole Q-brain story? I mean, I mentioned lithium as a motivator, but I haven't mentioned lithium. I've been focusing on phosphorus 31. Well, the way lithium would have to come into the story was if a central calcium ion is replaced by two lithium ions. And this turns out from density functional theory calculations is energetically favorable, and actually two lithium ions stabilize the Posner molecule. Now, once the lithium ions, if they get into the Posner molecule, they would modify the nuclear spins of the lithium ions would couple to the phosphorus nuclear spins, and particularly lithium-7 would lead to phosphorus 31 nuclear spin reaction and would affect the future bonding of pairwise bonding of the Posner molecules together. Now, if Posner molecules are, doped in by lithium, one would expect within this whole story a lithium isotope dependence on two things. In vivo, calcium phosphate sequestration in mitochondria, one should be able to see some lithium isotope dependence on mitochondrial calcium processing, and in vitro, in calcium phosphate precipitation in a test tube. So let me just very briefly show you those two experiments, which both showed a remarkable lithium isotope effect. So in this experiment done in Munich with a collaborator, Tobias Fromm, mitochondria were isolated in solution and kept functional. If you add a lot of calcium in, then the calcium gets gets sequestered into the in the mitochondria. And if you add too much in, after a while, in timescales of minutes or even half an hour, the calcium is suddenly extruded. It's released, and it undergoes a permeability transition. So what was done was to bathe the mitochondrial solution with lithium-6 or lithium-7, and this was very reproducible that the lithium-7 mitochondria with lithium-7 absorbed released the calcium more quickly, and lithium-6 held the calcium for longer. So lithium-7 induces a more rapid release of calcium than lithium-6. So this was what we expected to find some differential lithium isotope dependence here, and we found it. Now I wanted to note that some nice experiments by Zoe Leonenko and Michel Gingras at Waterloo showed no lithium isotope dependence on the uptake into the mitochondria. So it's not a question of more lithium-6 or more lithium-7 getting into the mitochondria. It's actually some sort of functional role. And the final experiment, which we're just finishing up, is looking at the amorphous calcium phosphate precipitation in vitro. So here we basically just take water, we throw in sodium phosphate and calcium chloride, I think it was, plus some other sodium and potassium ions. And then what happens under the appropriate pH, which is pH is not too low, pH is in the 7 to 8 range, is that the sodium, usually the phosphate and calcium ions start bonding together, and under some pH range form, we think, these Posner molecules. Under other pH range, calcium phosphate nanoclusters. And if the pH is not too low, these Posner molecules start clumping together. They form these larger clusters, the amorphous calcium phosphate clusters, which then continue to grow and form colloidal aggregates. And one can measure how many of these colloidal aggregates are present at different sizes when one runs this experiment in a test tube using dynamic light scattering. And so the question was, could lithium incorporation into the Posner molecules influence the formation of the amorphous calcium phosphate aggregates? And so this is what we did. We took these solutions with these calcium and phosphate concentrations and put in lithium chloride, either lithium-7 or lithium-6, and use dynamic light scattering as a function of time. The horizontal axis here is in seconds to measure the diameter of the growing clusters of calcium phosphate, and there's no difference here. either a pH of 7.5 or a pH of 8.1. So that was rather disappointing. But if you look at the actual total intensity, the scattering intensity, not just the size distribution, then at 7.4, even though it's noisier, there wasn't a lithium isotope dependence. But in the pH of 8.1, there was an appreciable lithium isotope dependence. The scattering intensity here, I say, shows a lithium isotope effect. So you get higher scattering intensity for lithium-7, and that indicates more large calcium phosphate structures in lithium-7 solutions. And you can ask at which step of the amorphous calcium phosphate growth does the lithium isotope effect manifest itself. This step 1 is basically going from step 1 to step 2. The calcium and phosphate ions, start clumping together to form either Posner molecules or another tricalcium phosphate. And then those cluster together to form these larger ACP clusters and then form colloids. So we can do NMR, phosphorus 31 and lithium-6 and lithium-7 NMR, and that indicates no difference in the ionic interactions or water structuring, which is perhaps not surprising. So we can rule out lithium isotope dependence in step 1. We can look also at NMR, lithium-6, lithium-7 NMR, and phosphorus 31 NMR, and we see the similar incorporation into the amorphous calcium phosphate clusters for both lithium isotopes. And so that leaves just this step 2 to step 3, and there the lithium isotope dependence occurs at a pH, slightly higher pHs, which is where the Posner molecules are found to exist. So the lithium isotope effects appear to be active in the aggregation of Posner molecules into calcium phosphate aggregates. So this is sort of just a schematic of what we think might be going on. We have in solution these Posner molecules forming. As a function of time, they tend to cluster together to form these larger aggregates. But then when you have lithium-6 or lithium-7, that speeds up the aggregation, and empirically, then lithium-7 speeds up the aggregation the most rapidly. That is, lithium-7 causes more rapid, in fact, pseudospin decoherence and fewer pseudospin restricted binding events. And so this is what we would expect. We're expecting to see more lithium-7 large aggregates than lithium-6. And so that was rather nice. Okay, let me just start wrapping up. A little bit of humor I'm going to inject. So there was this movie that came out a number of years ago called Ant-Man and the Wasp. It's one of the Marvel movies, I think. Here's Paul Rudd, one of the actors in that movie. And then it was about, ants and wasps becoming very small and people becoming very small and going inside the brain. So let me just play this for your amusement. Okay, so it's incredible. You're linked to Janet. Here we go.
It's incredible. You're linked to Janet. It's quantum entanglement between the quantum states of Posner molecules in your brains.
Yeah, that's what I was thinking. Do you guys just put the word quantum in front of everything?
Okay, well, I'm a quantum physicist, so I do put quantum in front of everything, and I've been doing that in the cognitive context as well. So let me just summarize the experiments and then talk about more general implications or issues. So Posner molecules are stable in solution. There are lithium isotope effects across many scales of size and complexity. I haven't talked about neuronal cellular impulses where there's a strong lithium isotope dependence, which has been observed. We need to check this quantum dynamical selection. So let me come to consciousness, which for me is a rather slippery slope. And in fact, some, if not most physicists think consciousness, either it doesn't exist or it is not definable, or maybe just simply it's too mysterious to be understandable. And this is Ed Witten, who's one of the most famous living theoretical physicists, string theorist. I'll read it. Biologists and perhaps physicists will understand much better how the brain works. Well, that's certainly true. But why something that we call consciousness goes with those workings, I think that will remain mysterious. I have a much easier time imagining how we understand the Big Bang than I'm imagining how we understand consciousness. Well, okay, maybe that's a bit too pessimistic. But some other physicists think that quantum mechanics can perhaps be ruled out, and this is a colleague of mine at MIT, Todadri Senthil, and he says the general assumption has been, but of course there is no quantum information processing that's possible in the brain. He, meaning me, makes the case that there's precisely one loophole, which is nuclear spins. And so the next step is to see if that loophole can be closed. Well, what we've been trying to do is close the loophole of phosphorus 31 nuclear spins being operative. And at this stage, we have not closed the loophole. So let me return to sort of the title, is Are We Quantum Computers? Another famous physicist, Nobel Prize winner, said to me, well, Matthew, I don't think evolution is clever enough to evolve a quantum computer. And so I started thinking about that. Well, what's the history of quantum computing? Well, it started in 1982 when Richard Feynman made a suggestion. It got an impetus in 1994 when Peter Shor developed an algorithm that could be used for quantum code breaking. And since then, there's been a lot of progress in industry. This goes on up to 2025, where Google and IBM have operational quantum computers with maybe 50 or more qubits. But it's slow work, and it's very, very complicated to isolate and control quantum systems. So one might ask, how long will it be before one has a multi-purpose quantum computer? Maybe 50 years. But then I said, well, if they're thinking about evolution, let's take a longer path towards evolving a quantum computer and start really 3.5 billion years ago, where life, single cellular organisms started evolving. Evolution continued over the millennia, and eventually reptiles, mammals, and humans evolved. So evolution has had a long time to do remarkable things, of course, as we all know. So 3.5 billion years is long enough, apparently, to evolve human quantum engineers that work at Google. So since Google is now building a quantum computer, evolution has found a path to making a quantum computer, even if it's going through classical humans. So then one can ask, how many years will it take for evolution to design, build a quantum computer? Well, maybe it's 3.5 billion years plus 50 years. But maybe it's just 3.5 million years. Maybe we already have quantum processing in our brains. And if B is correct, then one can ask, well, what's the best way to build a quantum computer? And the answer is not for the males in the audience, but for the women, just get pregnant. Grow a quantum computer in your womb. So let me come back to consciousness again, and sentience. Is it classical or quantum? Now, I, like probably everyone else, has been totally blown out by ChatGPT. I mean, it's a pretty amazing classical, I call it robot. ChatGPT has 1 trillion parameters, 1 trillion numbers, which describe it. And that's the same roughly as the number of neurons in the human brain. But Chat basically stores and manipulates classical information. It's just a classical information processor. And it's manipulating ones and zeros, that is, bits. Now, could Chat become sentient? And I know people are starting to think about this question. And maybe even if Chat, GPT-4 is not sentient, maybe Chat, some future version, maybe 57 would be sentient. We of course don't know, and it's of course hard to determine whether or not Chat would be sentient. Or might sentience require storage and manipulation of quantum information? Maybe it's possible. It's the situation that it's in fact impossible for a classical information processor to develop conscious awareness and sentience. Maybe that requires quantum information processing. And if that were the case, maybe in some future distant future with Google or maybe the IBM quantum computers, maybe they could then become aware. Okay, so I've basically run out of time. Let me just end with an acknowledgement. Most of this work has been supported by the Heising-Simons Foundation. This work has been done at UCSB, Waterloo, and Munich. And let me just in particular emphasize two graduate students have been absolutely pivotal, Josh Straub and Manisha Patel. And let me stop there and thank you for your attention.
Thank you very much, Matthew, for that fascinating talk. What I'm going to do now is firstly announce the result of the poll. So let me end the poll and share results. So the poll was answered by 84 participants. Not all of them answered this, but 84 is quite a reasonable number. The first question was, despite being warm, wet, and noisy, the brain could harbor quantum information. 82% of these participants answered it as yes. So Matthew, congratulations. I think all your work is becoming world famous and they're actually buying into your
Yeah, but we're
theories.
not, but science is not a democracy, so I'm not sure that matters too much. But let me just comment on the first question. Despite being warm, wet, and noisy, the brain could harbor quantum information. Certainly, quantum information is being held in nuclear spins in the brain. The question is, can there be quantum processing of information? That's the real question. Now, of course, for the second one, if mental processing may be associated with quantum phenomena, there has to be quantum, I assume that means processing of quantum information. So anyway, that's a rather
Right. So
encouraging.
81 was yes, which is quite impressive as well. And
Yeah.
maybe while the questions are trickling in, of course, I'd request Christoph to maybe ask one quick question. But in the context of mental phenomena, right, like thoughts, qualia, of course, quantum processing is one thing. But then we are still not closing in on the gap to resolve this hard problem. Like, how is the correlation between these mental processes occurring along with either quantum processes or neural processing, whatever it might be?
Yeah, so that's really a separate question than what I'm asking. I mean, asking the question, can a classical information processing unit become sentient and aware and develop qualia, I think is a well-defined question, although it doesn't tell us what, how even if it's possible, it wouldn't tell us how that actually occurs. It doesn't really define what qualia is. But I think the question of whether a classical information processor could become sentient and conscious, I think that's a well-defined question. And if the answer is yes, that's okay. And if the answer is no, you can ask then, could a quantum information processor become sentient? And maybe the answer would have to be yes for that, presumably, assuming that we all agree that we have consciousness.
Whatever the answer, your work is absolutely fascinating, Matthew. I'm going to request Christoph if you have a very quick question, and then we'll go on to the participants' questions.
Well, you say this is a well-posed problem. I'm not sure, because it really depends on a theory of consciousness, right? Clearly, we can all agree ChatGPT is very good at pretending and doing fake consciousness, right? You can ask it how it feels, and it'll give you detailed information how it feels at this moment, because it's been fed humanity's collective output and novels and writing, and those are mainly about people's conscious experiences. So what we need is a theory, a general agreed upon theory that tells us this piece of highly active matter is or does not or does feel like something. In the absence of such a theory, I think these problems are not well posed. But I totally agree with your main point.
But Christoph, what would such a theory even look like in principle?
Well, I mean, there are certainly candidates around. Integrated information theory, for example, is a very well precise theory. It's an operational theory. It starts with a particular system in a particular state and precisely derives a calculus to show what if the system is conscious and what is it currently conscious of. Now, you may not be a fan of IIT, and that's fine, but this is one working example of a very precise theory that bypasses a hard problem because it starts off with consciousness. But I think more interesting about your question is, which is, I agree, a purely empirical one, does the brain or does the brain not use quantum entanglement to process information and access cognitive states? I think that's an eminently purely empirical answerable question.
Yeah, and that's a question we've been seeking to answer. I was mostly throwing in some speculations about consciousness in the.
I totally agree. And so there, my main challenge is, assuming everything you say is true, particularly if you look at large brains, like the brains of all mammals, it's even bigger case when you have an elephant or whale, right? They can be, this big. So you need to coordinate. We have the thing called the binding problem, right? I can be conscious, aware of information that combines both color, let's say, and motion information, right? If I look at your hand or your head moving about, what I perceive is both color and motion, just a simple example. And we know those are kept in that information is distributed in different brain areas. So we have to somehow bind this information at the time scale of, let's say, 100 milliseconds, 50 milliseconds, 100 milliseconds, something like that. And so that really requires a cross neuronal synchrony. And so, yes, even if everything you say is true within neuronal entanglement, how do we combine that? Aren't we forced to combine that information in classical ways?
Well, I mean, ideally, one would be able to get interneuronal quantum entanglement, and that would be, the most appealing. I'm not sure how to do that. I mean, there have been other suggestions using biophotons, and I'm a little skeptical of those, or sort of electric field fluctuations coming from mitochondria. I don't see that as transporting quantum information. So this is, I mean, an issue. I mean, and I'm aware of the experiments which show that conscious state seems to be very distributed across the brain, as you're saying. And if as I say, so ideally there would be some way to get into the different parts of the brain quantum entangled. Otherwise, it would have to be classical correlations being generated by measuring neuronal quantum effects, basically in each neuron, and then bringing them together. I mean, you asked me a good question about the interneuronal quantum entanglement, and I don't have a good answer to that. I mean, I think at this stage.
I'm going to suggest that we move on to a few very quick questions from our participants. This one is from Venkatachalam Anantran from Berkeley. He asks, might there be biological mechanisms that can maintain entanglement coherence over macroscopic timescales analogous to how quantum coding systems can correct errors?
Yeah, I mean, well, so the decoherence times for phosphorus 31 nuclear spins in Posner molecules could be hours, right? So that's already, pretty long. But to maintain quantum coherence for timescales, on days, weeks, months, and years would have to involve some active quantum error correction in some ways. Now, quantum error correction is something that scientists in quantum computing labs and are thinking about. And I mean, my view on that would be that the classical information processing that's surely going on in the brain and biological systems at all scales could have evolved to control the quantum information in these Posner molecules, to control it and maybe even do error correction on it. I don't have a detailed of how that could work, but we have a powerful classical system, of course, the brain itself to control possible quantum information.
Excellent. This next question is from Daniel Palanker from Stanford. He asks, what is the process of converting nuclear spin state into the action potentials in neurons, if at all those are linked?
Yeah, so the idea is that the polymer molecules inside mitochondria are going to be becoming entangled, and mitochondria are splitting and maybe going to different synapses. And then at some point, the calcium, which is being taken up into the mitochondria, has to be released as free calcium ions. And to do that, you have to dissolve or dissociate the amorphous calcium phosphate of the polymer molecules in the mitochondria. Now, if the mitochondria and the ones that are near the synapses release of calcium, I would suggest that can lead to neurotransmitter release in the absence of an action potential and could trigger a downstream neuron to fire. I don't know whether there's evidence for that, but that would be how the released calcium would have to trigger neurotransmitter release, and that's the transduction from the quantum mechanics to the neuron firing.
Very interesting. You made a curious reference to microtubules at one point in the context of mitochondria. There is one of our participants who would like to know how your theory is related to Roger Penrose and Hameroff's OR theory and what you think about that theory.
Yeah, I don't really want to opine on what I think about it. I don't think it's related at all. I mean, ultimately we need to identify, if there is quantum mechanics, the neural qubits, the quantum substrate upon which or within which the quantum information is being held, and nuclear spins are not microtubules. And I mean, I don't see how microtubules are going to be isolated enough from the environment to keep any sort of quantum coherence at reasonable time scales, or at any even very short time scales. But it's a hard problem, and I don't want to be too opinionated on this.
Sure. Maybe two maybe very rapid questions again, final ones. So what exactly do you think could qualia be, and could we develop a theory of qualia mathematically in the context of, let's say, quantum processing?
I don't know what qualia is. I mean, I know that I experience it. I don't think the way we're going to understand consciousness is through a mathematical framework. I think we're going to have to understand how to control it. To understand something, you need how to control it, how to modulate it, how to modify it, how to turn it on or off. That's why anesthetics, I think, are extremely important, actually. So I'm somewhat skeptical that we're just going to be able to write down some mathematical theory and say that this phase would correspond to an emergence of qualia and this phase wouldn't. I'm not optimistic that is the best approach.
All right.
I think to understand something, the proof of the pudding is in the eating. I mean, if you understand something, you know how to control it, right? I mean,
well, what about the Big Bang? We don't quite control the Big Bang.
Well, but on the human scale world with physics, we understand semiconductors and we can then control them. We understand superconductors and we can start building quantum computers with those. So you need, that's where understanding comes from, and sort of the proof of the understanding is that one really has the control to modulate the behavior that one's experiencing or observing.
All right, fair enough. One final question. Quantum processing and consciousness and reality being quantum, right? And this whole problem of quantum gravity being unsolved, and we know Roger Penrose connects free will with quantum gravity and so on. What is your take on what is consciousness, what is free will, and how is all of this connected with external reality, what
Well,
we
I don't think quantum gravity is
physical
at
world?
all relevant to these questions, actually. But the mystery, the biggest mystery in quantum mechanics, I think the biggest mystery in science, besides what consciousness is what constitutes a quantum measurement. How is information extracted from a quantum system? And when I teach quantum measurements in my quantum mechanics class, I challenge the students to tell one what a measurement is without using a pronoun. Because it's always when the experimentalists, when you measure it or they measure it, we don't know when a measurement takes place. We don't know what a measurement means. We don't know what it means to extract information out of a quantum system, unless we treat the observer as a classical entity. So I think that's where the mystery lies, is in what is a quantum measurement, how is quantum information manifested, and I don't think, yeah, and that mystery, I mean, I'm not the first one to suggest that the quantum measurement problem and human awareness and consciousness are somehow linked, but I think that's not crazy to think about.
All right, very nice. Any final remarks from your end, Christoph?
Thank you very much for a beautiful seminar, insightful seminar on qubits in the possibility of qubits in the brain in the form of pulsar molecules.
Yep,
Yeah,
fascinating indeed. So let's close here, since we've crossed our 1 hour the threshold, and the next colloquium in the Consciousness and Reality series will be held in the coming weeks. So please stay tuned for more information on that. And finally, I'd like to thank again Matthew Fisher, our co-host Christoph Koch, and all organizers and participants who made this event happen. Have a great day, everyone.
well, and I'd like to second that. Thank you, Kunal and Christoph, and anybody that tuned in. I really appreciate it. So thank you.
Thanks
Big
again.
question we need to answer one way or the other.
Absolutely. That's what this series is about. Yeah, let's get together and do something. Make a change happen. All right. Take care, everyone.
Okay, bye-bye.